Yeah, thank you very much for giving me the opportunity to give a talk here. I have to apologize for, I think, at least 2 people who have been already in Oldenburg. I gave a very similar talk, but I hope you don't mind. Yeah, first of all, it's a joint work with my PhD student, Sebastian Zimmer. And it is about some classical analysis in convergence of operators. And maybe you, those of you know me out longer, I've talked about long time already about what I called generalized non-resolvent convergence. But unfortunately, I learned only recently that there's a similar concept by Weidmann. I learned from Sabine's paper some years ago. And then we tried to find out what are the relations of these two concepts. Okay. Here, this one is it. Okay. Where to switch? Okay. Okay, let me just, I mean, maybe I don't have to talk much about it here, but let me just explain a little bit about motivation. I mean, you want to define some convergence of operators in a Hilbert space. First, it's a fixed Hilbert space here. And, well, if the operators are unbounded, okay, you use, for example, resolvents, yeah? And then you have bound operators and you can say something about convergence. In my case, to make life simple here, I take operators non-negative. I mostly have Laplacians in mind and such things. You can do it for self-adjoint or even for non-self-adjoint operators. It also works. And okay, you know this notation here. A non-resolvent convergence if the resolvents difference converge as n goes to infinity, and you can make also precise order here. And strong resolvent convergence if it's a pointwise convergence in the Hilbert space here. Well, this is everyone knows, yeah? And consequences, you know what you can do, then you can take functions of your operator. If you're in a self-adjoint case, this is easily defined for large class of functions. And for nice functions like the heat semigroup, you can even precise the order here, how fast it converges, or for spectral projections. And you have convergence on compact intervals, like a sort of an eigenvalue is in the limit spectrum if and only if you have a sequence converging to it. And you also have convergence of discrete spectrum and essential spectrum separately. Well, you know, Sabine is the expert on this here. You know, if you only have strong convergence, you might have that in the limit space, okay, you find a sequence. But you might have so-called spectral pollution. So this might be wrong. And I give you a very simple example. So take H equal L2 of 0 infinity and H n f x, you take x over n times f of x. Then the spectrum of Hn is just multiplication by x, but it gets less steep and steep. But it's for each n, it's 0 infinity, and the limit operator is just 0. Yeah. And if you take now the resolvents, Rn, well, the resolvents just by spectral calculus, you just write down here the corresponding function. It's 1 over x over n plus 1. So it's not negative because I'm in 0 infinity only, minus 1 squared f of x. And you can easily see that this function here converges to 0, but not uniformly, of course. So you have strong convergence here by Lebesgue theorem, yeah, but not non-resolvent convergence. And you see, okay, the limit here suddenly shrinks, yeah, from the half line to the point. So this is why, at least in my case, I'm mostly interested here in norm-resolvent convergence. And yeah, now the point is now, what do you do if your Hilbert spaces change? Yeah, and I mean the one natural idea is what happens if you have subdomains x n, and everything is embedded in some big space. Let's say shouldn't call it R n R d. Sorry, n is already given. And you'd have, in some sense, you want that, let's say, a derivative Laplacian or something, and maybe this somehow converges in some sense to some limit domain, not necessarily included, could be both situations. And yeah, how do you define somehow convergence here? Well, here it's very natural here in this situation because everything is embedded in a big space. Yeah. So what you do is you just take use isometry like the L2 space of Xn, embed it into L2 of Rd via some isometry. You extend functions by 0. Yeah. And if you take the adjoint of the isometry, it's just the restriction to this subdomain. And then what you do is you just compare the resolvent sandwiched by this isometries in Actually, an adjoint of an isometry is also called co-isometry. Yeah. So like this. And actually, this is somehow a very natural approach because this is what you would call a pseudo-resolvent. If you have the spectral parameter inside, these functions still satisfy these resolvent equations, and they are real resolvents if and only if they are injective. So this concept actually is by Weidmann. It's a little bit hidden. I mean, Weidmann, I think, had in mind already these domain perturbations. And it's a little bit hidden in it's in his German book on some in 2000 in some subject section where he defines this. Okay. And well, a simple case is, for example, if everything is embedded, not like this situation, but if xn exhausting x infinity, so it's a subset of x infinity, then you can just use as common space here, or we call it also parent space in our article, the L2 space of this outer one here. Okay. And this good thing about this Weidmann situation here is you can also easily define strong resolvent convergence because you just ask that these functions converge pointwise to 0, the difference, yeah? Maybe most of you, those of you who know me already before, my favorite topic is just like these thick graphs, yeah? Like you have, well, I'm not to talk about thick graphs today, but you take, in the limit space, you have somehow here a metric graph, and take, let's say, the Kirchhoff Laplacian on it, and you want to know if you have a domain approximating this set, like with epsilon here, and this is of order epsilon if it shrinks, and you want to compare somehow if epsilon goes to 0, convergence of, say, Neumann Laplacian here to this one, to the Kirchhoff Laplacian, and there you have very different spaces, yeah? This is an L2 space on lines, on intervals here, and this is L2 space on a subset of R2 in this example here, and of course they have basically, first of all, no relation. And well, what we do here, an old paper also by work with Pavel Exner and some works before, we showed somehow convergence in the setting. And this is what I also call it a generalized non-resolvent convergence. I added here QUE not for quantum whatever ensemble, but this means here quasi-unitary equivalence. I come to this in a moment. Well, the order is only a square root of epsilon. I comment on it at the end. And yeah, question? Yeah, of course, sorry, yeah. Daniel Grieser did something in a very general way. Yeah, sorry, of course. This is he did the Dirichlet case. He showed especially the precise order of the eigenvalues, and he showed it as of order epsilon. We work on this now to generalize, and I think we finally find a way, or at least I think we can do it. I say a few words on it at the end, yeah? Sorry, the list is a bit incomplete here. Okay, what is the concept generalized non-resolvent convergence in my setting? I mean, you take again here your resolvents. Here's an epsilon inside from the problem before. And you have identification operators from the limit space to this one. Like you take your functions and you extend it transversally constant, you put 0 here. And we say that it's this generalized non-resolvent sense convergence in this QUE setting, quasi-unitary equivalent, if and only if you take this identification operator, put it in both ways, yeah, and compare it to the identity. and you weight it with the resolvent here, and you want this to be small, and also the resolvent difference sandwiched, yeah? And apparently this definition looks very different than Weidmann's one, yeah? First of all, here it's not clear what to use as a common space. And second, well, here's no reference to some common space here, yeah? So let me come now back to the notation before with the sequences. So I take a sequence epsilon n to 0, and for some reason I have to take adjoints here. It goes the other way around. So the definition here to compare it with Weidmann is this way now. The same thing here. You have some the resolvents, how close they are to unitary map, and with the resolvents here. And if 1 and 2 holds, we also say that these operators have sort of a quasi-unitary equivalent with a delta n. So we somehow quantify how far away are we from unitary maps. Yeah. So if, for example, for 1, if delta n is 0 here, then of course it means this has to be equal here. This also, so Jn is unitary. And then without loss of generality, you can choose the same spaces and Jn identity. Then you just end up here with classical norm-resolvent convergence, yeah? And if delta n is for both 0, then it just means that your operators are unitary equivalent. So if this is equal here, then it means also if this equals 0, then this the operators are unitary equivalent. Okay. So here's again repetition of the generalization, generalized norm-resolvent convergence in my setting here. And yeah, okay, sorry. You can also do the same thing as before. For classical one, you take just functions of operators, sandwich them with this identification operator, and you also get convergence. Yeah, this is just look at the classical proofs and try to take it over. It's a little bit difficult because you have to always add up these operators, but it works. And the spectrum converges the same as classical norm-resolvent convergence. Yeah. Okay. Yeah, okay. So this is just a repetition here. For some reason, you will see later, I want the operators to have norm less or equal to 1. And what is now Weidmann's concept again? Here, yeah, you embed everything in a common space. And you want the resolvents embedded in the big space, the difference to be smaller than an order, yeah? I have to say that Weidmann originally said that all the spaces are subspaces of a common space, but if we do this strict setting here, then we cannot compare them because our spaces are really different. So we allow isometries, and it has a disadvantage also. For example, you could add some unitary operator here and somehow mix it up. It would be still convergent. It's not, but you cannot avoid it. Oh, what's happening here? I think not so important. Okay. Let's continue. Now compare both concepts. So the main result now with my PhD student, Sebastian Zimmer, is that both convergence are actually equivalent. Yeah? And, well, here I repeated it. This is a quasi-unitary equivalence with delta n going to 0. And here Weidmann's concept. And for further references, I call the difference of Weidmann's resolvent, the generalized resolvents here like this, dn. And there's an easy way. Yeah, if you go from this concept of, from Weidmann's concept to this concept, it's not difficult because what you do, let me write down here the spaces. I mean, it's quite natural. You have the h here. You have in, the hn, and here you take the adjoint of this one, and then you need somehow to come h infinity. You need to define some sort of j. In my setting, this identification operator, you just take jn to be the right order, iota infinity, iota n. And, well, then, this one here. And then what you actually do is you try to express, you need to show that these quantities are small. You try to smuggle in your dn here, because this is small in norm, yeah? And actually, it's not hard to see that you can do it like this. For example, if you take this one here, iota n, first of all, you define some projection in the big space. It's just the other composition of the isometries, co-isometry. This gives a projection, you can see. And let me just try star like this. P infinity is identity minus iota infinity star. And then you take dn. And we have a iota n here. And first observation is, once you have this orthogonal projection here to the infinity space, to the image of H infinity in the big space, and you come, iota infinity comes here, then this would be 0. So only the n term survives here. Yeah, only this one here. So here you can just forget about the infinity term, it's just iota n, Rn, iota n star. And also in isometry, let me take colors here. Isometry is defined, for example, you can define it like if iota n matches the other one here, the adjoint, it's just, you can just cancel it. So what's happening actually here, you get here iota n, you get again the same setting here, you can forget about it, In on Hn minus, and here you get iota n star, infinity, iota star, iota n, Rn. And here you recognize actually our Jn, yeah, Jn and Jn star. Actually, it's not a very easy exercise, not hard to see. And so you see that actually this equality holds here. Yeah, for example, the other one is the same, and this one is even easier to see. Let me mention, if you look in Weidmann's book, for example, or I think Sabine uses also the Weidmann convention, there you don't distinguish much between the big and the small space. But since we have different spaces here, we really needed somehow to give these names to this in isometries. Otherwise, I don't know. We tried in the beginning. We did a bit bad job here. Now if you see the formula, it's very easy to see what you're looking for. But in the beginning, we had some trouble to find the right formulas. So then, this takes norm here. All these operators around the dn are norm equal smaller to 1. So it's just actually, you get the same order. If Weidmann convergence holds, then this convergence holds with the same conversion speed. So here, dn, then it's the same speed, yeah? So this is very easy. And now, I'm running out of time, but don't worry, you will get coffee break soon. The other direction, what is difficult here? Well, you have no reference here to a common Hilbert space, what we call parent space, yeah, because everything lives, think of the thick graph example, yeah, it's not clear what's the common space here. And also, not only you can find some common space, takes the direct sum of all spaces, but then, yeah, you need factorization of your JNs. The direct sum would be very bad because then you would compare the different resolvents in different spaces. They had no relation at all, yeah. And what you do here is actually you write dn, you smuggle in these projections onto the images of the. Okay. First, you assume you have such a space, yeah. This here, step two. Here is it written here. You assume it exists, and then you write down dn as this. The fourth term doesn't appear because, as I said, if you have two orthogonal complements, they cancel out as a 0, yeah? And for example, you have equality here. The last one is rather easy. This is just exactly the resolvent difference sandwiched. Oh, here's a Jn. This should be a Jn here. And the other one, you can also do similar calculations as here. It's just, this can be seen, the norms equal to the square root of this. And this plays a role later because we lose some order here. And, okay. So we have equivalence here. And there's a bit, as you see here, if in step 2 we assume we have this common space, and then if you have QE setting, we get this smaller to delta, but we have square root here, so we lose a square root, yeah? And then we ask ourselves, can we do better? And then we realized, yeah, if we have a parent space exists such that these projections commute, yeah, then the convergence speed is actually the same, the order, yeah. And finally, let me come how the main idea how to find this common space. Well, we need to say what is the partial isometry. Well, basically you restrict to the orthogonal complement of the kernel of it and to the image, and then you say to the kernel orthogonal complement it's an isometry. Or you say it's I star I equals I, for example. And we have now the following equivalent characterization. So it only depends on these identification operators. So if Jn is a partial isometry, if and only if for one parent space or for all, we have that these projections defined by these isometries commute. So in this case, we have a better convergence speed or the same. And let me finally come to the point. How do we define the common Hilbert space? And so I learned about this in this book here by Shane Nudge, that you take this operator, square root of it, and call it defect operator. And why you use this operator? Well, here, this equality is a key point. Yeah? And actually, Vn, Fn, Fn, sorry. Yeah, you have the square root here, you have identity minus Jn star. And now you easily see this is just the norm Fn squared minus norm of Jn. Fn like this, yeah? So this equality is easily seen here. And then you define your isometry, the common space, just a direct sum. And the infinity component is easily, you just put it in the right component. But the Jn component, you don't just take the nth component, but you take Jn here in the infinity component, and this operator here. And because of this equality, yeah, put this on the other side, you see the square of this, norm square of this equals the norm of Fn. So it's an isometry. Yeah, and this is clearly isometry. And this is our space. And also here, because Jn star just takes the adjoint, the first component here, so it's just sectorizes, yeah? So we are done. This is an example in the common space of the thick graphs. You take the orthogonal sum of it and take some funny component into the big space here, into the thick space. And equivalence now of the beta convergence speed. This is a partial isometry. The defect operator is an orthogonal complement, or it commutes. Other concepts, yeah, don't say much about it. Most people consider strong resolvent convergence and homogenization theory, but let me come to outlook. If you look, we've shown this quantity is actually equal to something in this Weidmann concept, one of the norms. So we could redefine the skew definition by this one, because first we only had this part is small, and maybe we take this one. And actually, funnily, this equation here is equivalent to beta n squared times the graph norm. Oh, I'm running out of time. Yeah. So, and finally, this is actually what we did in our first paper with Pavel. We compared the squared norms. And actually, this is, yeah, it's funny, this appears here again. So you could think of delta n as a sort of distance and use Weidmann's concept, for example, to define how far away are the operators by taking infimum over all isometries, all big spaces, all parent spaces, and so on. And the good thing about the equivalence is Weidmann's concept allows now also well, it's easily seen for strong resolvent convergence, and you could now use this equivalence to see how to define strong resolvent convergence in this other setting. Yeah. So thanks for your attention. Yeah.